Lab 4 Oscillations, the physics of extreme sports with ropes. The goals of this lab report are to analyze the motion of an attached mass as it oscillates on a spring, to plot data in Tracker based on video, to make a computational model of the spring using VPython, to graph the components of delta E using the energy principle, and to analyze results through what does it mean questions. Before we discuss the models created from this video, it is important to discuss physics concepts illustrated by this lab report. Let's start with the energy principle. In this example, the only components that make up the energy principle are kinetic energy, gravitational potential energy, and spring potential energy. All those add up to the change in energy. We also know that since there is no outside force acting on our system, or outside work being done, that the change in energy is zero. Even though we know that delta E is zero, it is important to be aware of the components of delta E and their values, so we can later write the code for the computational model. Delta K equals 0.5 mv squared, delta UG equals mgh, and delta US equals 0.5 ks times s squared. It is important to note that we do not know all of these values immediately. Some have to be calculated based on model data. That will be discussed later in the lab report. Now let's discuss our first step, analyzing the video in Tracker. You can see that as the video plays, teal circles appear on the center of the screen. This was done manually to track the position of the mass. You can also see on the right-hand side the graph of the position in the x direction versus time. We will look at this closer later in the lab report. The next step is to make a computational model of the video using the data we collected here. Here we can begin to make a computational model of the video. Let's begin writing the necessary code. As I mentioned earlier, parts of the energy principle calculations are unknown and we must solve for them. Most importantly, we don't know Ks, the spring stiffness constant necessary in computing delta US. This calculation is shown in the upper right-hand corner. We must first calculate T, the period of oscillation. By looking at the graph from Tracker, we can mark the troughs of the position curve. This is shown in the bottom right by the black lines. We can take the average differences to get T, which is 1.634 seconds, and then solve for Ks, our stiffness constant, which turned out to be 5.944 newtons per meter. Next, we need to calculate the relaxed length of the spring. In the delta US equation, S stands for the change in length of the spring. It's the difference between the known length of the spring, 0.7 meters, and the initial length. We also know at static equilibrium that the magnitude of the spring force equals the magnitude of the weight force. By substituting the values, we end up with a value of 0.0372 meters as the relaxed length of the spring. Here's a summary of all the data that we know. This will all become important as we continue to write the necessary code for the model. Next, in our code, we need to include the components of the energy principle. We can see here a direct comparison with the difference of different components alongside the necessary lines of code. Also, shown at the bottom, we can implement calculations for changes by using delta K, delta UG, and delta US. It is important to note that we can run our model to graph two different data sets by just making a few minor modifications. Let's just focus first on seeing the model with a graph of oscillation positions. This is shown here. The blue line is the computer model coded for, and the red line is the graph found from Tracker, how the mass of the spring was tracked. It is important to note potential sources of error here. Obviously, the red and blue lines should match up completely, but they don't. This was due to the difficulty in tracking the position points in Tracker. However, the model is a fairly good approximation despite errors. The second graph from the model focused on showing the different components of the energy principle. This is shown here. The blue line is a change in kinetic energy, delta K. The red line is a change in spring potential energy, delta US. The green line is a change in gravitational potential energy, delta UG, and the yellow line shows delta E. The fact that delta E is zero, a zero straight line, proves the energy principle's validity in this example. This is the result that we predicted from the beginning. Now I will address two what does it mean questions. The first one is, for your model system, is the energy principle satisfied? Remember that the energy principle equation is delta E equals delta K plus delta UG plus delta US equals 0. In this example, the energy principle is satisfied. If we look at the graph from the model of the different components of this equation, we should focus on the yellow line, which is strictly along the x-axis. That is delta E, which is an addition of all the components of the energy principle, which all add up to 0, satisfying the energy principle. My t in the x position after calculation was 1.634 seconds, and my t in the y position was 1.5 seconds. These are extremely close, indicating that the mass of the object was oscillating just as much in the x direction as it was in the y. However, my xt value is slightly larger, meaning that the mass was covering more distance in the y direction faster than it did in the x. In conclusion, we can see that this lab was a very good example of the energy principle. By looking at the model predictions as well as the position data from Tracker, I was able to prove the validity of the energy principle. Even though this system was only one spring with a mass attached, these principles can be connected to many other systems involving multiple springs. By simply making observations, we can calculate not only changes in overall energy, but changes in kinetic and potential energy as well. Thanks for watching.